In this video, we're going to talk about momentum and impulse. Let's start by defining what momentum is. The old physicists, the natural philosophers, would talk about an object's quantity of motion. And René Descartes famously talked about the quantity of motion as being the product of mass and velocity of an object. So imagine you have an object of some mass m and a velocity v, then you would talk about its quantity of motion as being m and v. Now, today, when we talk about motion, we mostly just talk about the velocity of an object, not the product of mass and velocity. So it's more common for us to call this quantity not its motion, but its momentum. And we use the letter p to represent the momentum of an object, and it would be a vector, because some people used to call this the impetus of an object, and it was something that you would impart. So like a cannon imparts the quantity of motion to a cannonball. So anyway, this is our definition of momentum. And the units of this are pretty straightforward. They're just going to be meters, m for mass, so kilograms, and then velocity, meters per second. Let's do an example. You throw a 0.06 kilogram tennis ball with a speed of 10 meters per second at a wall. The wall rebounds back at 9.5 meters per second. What is the change in momentum of the tennis ball? Okay, well, so let's kind of do a before and after situation here. Before the ball, it hits the wall, right? And it's traveling first to the right with a velocity, we'll call that v naught, of 10 meters per second. And I'm going to make this a positive 10 meters a second to remember that it's moving to the right. Afterwards, the ball is going to start moving with a velocity to the left of 9.5. So it loses a bit of this speed. And since it's to the left, I want to write negative 9.5 meters per second. Okay, so imagine you throw a tennis ball, it goes at the wall with 10 meters a second of speed and then rebounds back with 9.5. So what do I need to use these velocities for? Well, remember that the momentum of an object is its mass times velocity. And if I want to find the change in momentum of the object, all I have to do is figure out what's the momentum in the beginning, or p naught, which would be m v naught, and then the momentum at the end afterwards, or just p m v. Okay, well, this should be pretty straightforward and simple. The mass of the object is 0.06 kilograms, so 0.06 kilograms times a velocity of positive 10 meters a second is going to give me 0.6 kilogram meters per second. Okay, so that's the initial momentum. Let me separate these. The final momentum is going to be 0.06 kilograms times negative 9.5 meters per second, or negative 0.57 kilogram meters per second. Okay, so we've calculated the momentums, and remember, these momentums, they have directions. This is going to be a positive, so to the right momentum, as the object is moving right, and this is a negative momentum because the object is moving to the left. So what do I do to find the change? Well, the change of momentum is just going to be the momentum in the end minus the momentum in the beginning, right? Which we could write that if we wanted. Sometimes it's common to do this. Well, let me just do the numerical example, and then we'll talk about this. But the momentum at the end is 0.6 it's not 0.6, it's negative 0.57 kilogram meters per second of momentum, right? That's the final. And then I subtract the initial, which is 0.6 kilogram meters per second. And you'll notice I have a negative number minus a positive number, so I actually get a bigger negative 1.17 kilogram meters per second. So that would be the change in momentum. Okay, so here I also want to point out that you could solve this problem a little bit differently. Instead of finding the momentums, you could sort of do this all in one swoop by saying the change of momentum is p minus p naught, or mv minus mv naught. Now notice that the mass is the same in both things, so you can factor it out. and have v minus v naught, which is like saying m delta v. So to calculate that momentum, here I'll do this over to the right a little bit. You could do the mass, which is 0.06 kilograms times just the change in velocity, which would be at that negative 9.5 meters a second minus 10 meters a second, which would be a negative 19.5. And multiply that by the 0.06, and you'd get the same answer, negative 1.17 kilogram meters per second as the change in momentum. Again, the same thing that we got here. So there are kind of, a few different ways to write change of momentum. And that's going to be helpful for us when we're writing out a new equation with something that we call the impulse momentum theorem. So let's talk about that. The impulse momentum theorem is really just a reworking of Isaac Newton's second law. Okay, so Isaac Newton's second law, if you remember, is that the net force is the product of mass and acceleration. Okay, so the thing about Isaac Newton's second law is that we normally learn it in most physics classes as F equals ma. But that's not what Isaac Newton actually meant. When he verbally states his law, he says that the action impressed is proportional to the change of motion. And then he defines motion in the beginning of his book as the product of mass and velocity, just like Descartes would do. So really, what Isaac Newton is trying to do with his second law is say that net force is equal to mass times the change in velocity over a change in time. Okay, so the acceleration, that's what this is, change in velocity over a change in time. Now let's get to this place where Isaac Newton is talking about change in momentum, the change in quantity of motion. Well, you should hopefully recognize that this m delta v, that's like saying mv minus mv naught over delta t, or p minus p naught, right, over delta t, or the change in momentum over the change in time. So this is what I'm trying to say. Isaac Newton's second law really can be written as net force equals change in momentum over a change in time. Okay, now these are the exact same equations. That is what we are saying. So this is how you would sort of do problems with force and changes in velocities, that kind of thing. What we normally do is rearrange this equation so that we're not looking at it as force is equal to change in momentum over change in time. It's less common to approach physics problems. Instead, what we do is we multiply the net force by time, which gives us the change of momentum, delta p. Okay, so this is a thing. We say that the force applied for an amount of time, this guy right here, we call this the impulse, or the impact that an object experiences. And basically, we are saying that the impulse is equal to a change of momentum in an object. That is the impulse momentum theorem. Now, often you will see impulse, it gets even weirder, written as J. And you can say that impulse is equal to J if you would like. It's also okay for you to just do force times time. And you should note that the units of this are going to look a little bit different. The units are going to be newtons times seconds. And if I kind of write this off to the side, so a newton is a kilogram meter per second squared times a second, then what I get is a kilogram meter per second, which is the unit of momentum. So the units of Newton seconds of impulse is equal to kilogram meters per second of momentum. I know, so much just units and stuff and Well, what's the equation that we need? The equation that we need is the impulse equals change of momentum. we just expand the momentum part. When we expand the momentum part, then we say net force times time equals mv, the momentum at the end, minus mv naught, the momentum in the beginning. So either way, however you want to memorize this equation, this is probably the most common way that it's written down, and I would maybe write this really big in your notebook and then circle it 1,000 times and be like, this is the equation that I can mostly use to solve problems. So yeah, it's just like a lot of language, different terms in these problems. So let's do a couple to get this down. You throw a 0.06 kilogram tennis ball with a speed, oh, this looks familiar, of 10 meters a second at a wall. The ball rebounds back at 9.5 meters a second. Oh my gosh, same problem. Using a force sensor, you measure the average force of the impact to be 20 newtons. Ah, okay, so we'll call this the net force. How long was the ball in contact with the wall for? Ooh, so that wants me to find delta t. Okay, so let's think back to our before and after. We have the mass of the ball is 0.06 kilograms. The velocity in the beginning, v naught, was a positive 10. Remember that distinction because it's moving to the right. And then it rebounds in the opposite direction, so I have to make this a negative 9.5 meters per second for the velocity to the left. Okay, so does this problem give me enough information to solve for the amount of time? Sure, there are a ton of different ways that we can do this. Probably the easiest is for us to remember that the net force times time, the impact, is equal to the change of momentum. Right, that's the impulse momentum theorem. And if I want to write momentum in its longer form, it's going to be mv minus mv naught. Now that's the information that I have right here. So if I want to solve for delta t, all I need to do is divide both sides by the net force. And boom, I've got my equation for the change in time. And now I can plug in my numbers and start chugging away. But notice I'm going to do, again, all kinds of algebra here. On the top, I might actually do the little trick where I factor out the m. So what I get is mv minus v naught. That'll just make it a little easier for me in my calculating, and that's the same thing as saying delta v. So I've got m, 0.06 kilograms times v, which is negative 9.5 meters a second, minus v naught, positive 10. And divide that whole thing by 20 newtons. Aha, but if I think about the force that's causing this to happen, here's the wall, here's the ball, all smooshed. The ball is going to experience a force back, which means that that net force should be a negative 20. Doing so is going to give me a sensible answer, a positive answer for time. So remember, we already calculated 0.06 times negative 9.5 minus 10. That was the change of momentum of negative 1.17 kilogram meters per second. Okay, and then when I divide that by negative 20 newtons, first of all, I'm going to get a positive number, right? So it's going to give me a positive 0.058, which is nice. Well, actually, it's 0.0. We'll just round that to 6. Now, what do we do about these units? Well, remember, we showed earlier that a kilogram times a meter per second is the same thing as a newton seconds, right? This is the net force times time, and this is change of momentum. So instead of kilogram meters per second, I can think of this as a newton second, and then boom, I see how the newtons cancel out and leave me with seconds, which is good because that's what I'm looking for as the amount of time. Now let's use this impulse change of momentum relationship to kind of answer a question of how much force is experienced for the same impact. So that's what this problem is going to do. Two 70-kilogram crash test dummies are in a car going 18 meters a second when the car suddenly hits a wall. One crash dummy has an airbag and comes to a stop in 0.1 seconds, while the other does not have an airbag and comes to a stop in 0.4 seconds. What is the impulse experienced by each dummy, and what is the average force experienced by each dummy? Okay, well, let's start with A. The impact experienced is going to be equal to the net force times the amount of time, right? Or I can find that impulse by looking at the change in momentum, which would be the mass times velocity at the end minus the mass times velocity in the beginning. Or, if I want to factor it, m times v minus v naught. Now, I know those three things. I know the mass of each dummy is 70 kilograms, the initial velocity is 18, and the final is 0, right, because it comes to a stop. So let's do that. Let's figure out what the change in momentum, and therefore the impulse, right? I could call this J if I wanted to. So many letters. The impulse would be equal to, well, I've got 70 kilograms times the final velocity is 0 minus 18. Ooh, that's going to give me a negative impulse, which is fine, because if I think about the dummies, hitting the airbag, I don't know if that's what an airbag looks like, there would be a force that's acting backwards on them, so I should get a negative impulse. Okay, so negative 70 times 18 is negative 1,260 kilogram meters per second. Only for us, it would be more appropriate to use newtons times seconds, Newton seconds, for the impact, the impulse, or change in momentum of each dummy. So boom, we found it. That's the change in momentum, and therefore the impulse experienced by each dummy. So, but B, what about the average force experienced by each dummy? Well, the dummies experience this same force for different amounts of time. Okay, so I know that the change of momentum, the impulse, is equal to negative 1260. But what about the times? Well, the change in time for the first dummy with the airbag is 0.1 seconds, and the change in time for the second dummy is 0.04 seconds. So to figure out the force, okay, the force is equal to the change in momentum. Well, I know the change in momentum for both of them is negative 1260. So to find the force, I just divide that change in momentum by the amount of time. So the net force on the first dummy is that negative 1260 Newton seconds divided by the amount of time for the first one, so 0.10 seconds. Okay, so that gives me negative 12,600 newtons for the net force, our average net force experienced by the first dummy. And for dummy 2, well, I just need to use that same negative 1,260 Newton seconds, but divide it by the time that it takes without the airbag, which notice that this is actually a little bit faster. It's taking less time, so 0.04 seconds. This is going to give me a bigger number, negative 31,500 newtons of force. So that's the net force on the second crash dummy without the airbag. So airbag, and then no. So here we see the reason for airbags. They cushion the impact. They don't change the amount of force directly. What they do is they change the amount of time that the force is applied over. And so if you have more time for the impact to occur, then there's going to be less force, right? Because we have 0.1 seconds and then less force, 12,000. Whereas if it happens really fast, like 0.4 seconds, that's only, like 0.06 seconds of a difference. That still results in 3 times the amount of force experienced without the airbag. So oftentimes when we talk about impulse, we compare the force that's experienced in these different impacts. It's important to know that the impulse, the impact, is the same. We use that same 1260 for each force, but the force calculations depended on the time, and they differed greatly depending on how much time the force was applied for. Okay, so We did a lot in this video, but most of the problems that you're going to face are just language, the different names that you have for things, impulse, change of momentum, all of that stuff. So it helps to maybe write some of those things down and to practice as many problems as you can with these types of numbers, these quantities in them. And your grade in this video is over.